Hi, my name is John Lucero, and today we're going to talk about minimum spanning trees and an important problem known as the muddy city problem, which has applications in the design of communications, and even transportation networks. Suppose there was a city that literally had zero roads. This was especially painful for the citizens after it rained because the entire city became a mud pool where cars were stuck in mud and people would have to walk in mud to get anywhere. Realizing that the town actually needed roads, the mayor of Muddy City made the decision to pave the streets, but with a very limited budget, because the city was also hosting the Olympics that year. The mayor informed the citizens that two conditions needed to be met. Number one, a sufficient amount of streets needed to be paved in order to allow the citizens to travel from their houses to any of their neighbors' houses solely through the use of paved roads. Number two, the city would spend the least amount of money possible in buying the pavement stones used to pave the roads. Go ahead and try to find the optimal route that connects each of the 10 houses in the city using the fewest amount of pavement stones. Great. As you can see, this problem can be difficult if you do not know how to find the minimum spanning tree, which is, for a graph G, a tree that contains every vertex of G and has the least weight among all possible spanning trees. To try and solve this problem, let's use Kruskal's algorithm. To demonstrate it, we will use the following connected graph G. Kruskal's algorithm provides us with a methodology to quickly identify a minimum spanning tree from a connected graph. In step 1, we choose our first edge to be an edge of G with the minimum weight. For this example, we pick the edge AB, which has a weight of 1. For step number 2, we choose any remaining edge of G with the minimum weight. Hence, we can choose the edge DE, which has a weight of 2. For the following steps, we choose the rest of the edges based on the following conditions. We pick any edge of G with the minimum weight that does not form a cycle with any of the previously chosen edges. Thus, we can safely choose the edge CB, which has a weight of 3, and lastly, choose the edge AD, which has a weight of 4. We now have a minimum spanning tree for this graph G. Let's go ahead and represent the muddy city problem as a connected graph and assign weights to each of the edges. Using the steps in Kruskal's algorithm, we can start choosing edges of minimum weight. First, let's choose any edge with the lowest weight, which in this case is 2. Here we choose the edge FG. Next, we choose the remaining edges with a weight equal to 2 in the following order: BI, EJ, and CD. Now we can start choosing the edges of weight 3 that still allow us to have no cycles within the tree. Here, we can successfully choose EI, JF, HI, AH, and lastly BC. Now we have successfully created a minimum spanning tree within the muddy city. As you can see, we can definitely use Kruskal's algorithm to solve the muddy city problem and meet the mayor's conditions of building a route that connects all 10 houses using the least amount of pavement stones.